This is an introduction to the unit circle and why the unit circle is so important. Because I think a lot of people study the unit circle and learn what to do with it, but I don't think they quite often understand why they are doing it. Let's jump right into this. A unit circle is very simply a circle with a radius of 1. So the unit is 1. The circle is just a circle with radius 1. It's generally plotted on an XY Cartesian coordinate grid. And so what the idea of the unit circle is that we can imagine ourselves going around and around this circle. And as we go around this circle, we go up and down, but we also go left and right. And so if we think of it and we draw some triangle right here, let's just say here, we draw a triangle. The distance that we've gone up is y, and the distance that we've gone over is x. So we've gone x distance over and y distance up. And of course, if I come over, I could draw a triangle anywhere. I could draw one maybe right here. And then I've gone a distance up equal to y, and a distance over equal to x. And so why is this important? Because in reality, lots of things go around and around. You can even think of a piston of a car. If you have a piston in a cylinder, for those who are familiar with how an engine works, and it connects to a crankshaft, the crankshaft goes around and around, and the piston goes up and down. So it's useful to think about how far the crankshaft turns compared to how the distance that the piston travels. And what we end up figuring out is that if we look at this and we go around this circle over and over again, as we go up here, we're covering a lot of vertical distance in this section of line, but we're not covering much horizontal distance. And as we get to the top of this curve here, we're covering horizontal distance and not vertical distance. So then if we actually go and plot a series of triangles and we just do basic Pythagorean theorem math, we can figure out how far we go up and how far we go over. And if we plot this on a graph and we say, hey, if I've gone up the circle a quarter of the way, again, that's 90 degrees. And if I've gone halfway around the circle, we'll call it 180. And so I'm just going to write this in degrees because I think it's more familiar. And it doesn't really matter. You could write it in radians, right? But right now, I'm just going to write it in degrees. And I say, I'm going to go around this circle. So I'm going to start at 0. And I'm going to plot two things, my x values and my y values. So as I start going up this, y value goes up. So let's just look at the y value first. We're going to start here, and the y value is 0. So I'm going to put a point at 0. And as I start going up, the y value gets bigger and bigger and bigger, and it reaches a maximum when y equals 1. Remember, this is a unit circle. And then when I get to 180 degrees, it comes back down. And when I get to 270 degrees, it's at a minimum. It's at -1. And I get to 360 degrees, I come back to 0. Remember, this is just the vertical displacement. So I'm going up, up, up. I reach my maximum. I come down, 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 down. I reach my minimum. And now I'm coming back up. And if I think about it, I'm traveling faster in the vertical direction when I'm on this part of the circle and this part of the circle. So my slope is going to be the steepest when I'm at 0, 180, and 360. And in fact, here, as I go around the circle, my vertical displacement's changing very little. So as I get to this 90, I'm really coming horizontal. And I'm at 270, I'm not doing much vertical displacement. And if I just draw that out, and again, I could do it much more carefully, but the general idea is true, then I get my sine graph. because in this, my xy coordinate is really just the cosine of, we'll call it the angle theta, and the sine of angle theta. And that's where the sine curve comes from. I'm just going to plot as I go around the unit circle. I'm going to plot my vertical displacement as a function of the degrees around the circle. And of course, I could do the same thing with horizontal displacement. And if I start at 0, my horizontal displacement is 1. So if I'm at 0, my horizontal displacement is 1. When I get to 90 degrees, my horizontal displacement is 0, right? If I'm here, my distance along the x-axis, that's 0. And as I come to 180 degrees, I'm down at -1. I'm all the way over at -1x. And of course, coming back up to 270 here, I've gone back to 0 degrees. And up to 360, I'm back to a horizontal displacement of 1, exactly where I started. And again, as horizontal displacement goes, as I'm traveling this section, I'm not making much horizontal displacement. So my slope is approaching 0. As I get to 90 degrees, I'm coming fast through the horizontal. I go a little distance and I go a lot. So that's where I get my bigger slope. As I get to 180, again, I'm not making much horizontal displacement. I'm going up and down as I pass 180. So my horizontal displacement isn't changing. And again, as I reach 270 degrees, my horizontal displacement's changing fast. I'm literally going from left to right as I pass through this. So now I'm back to here. And I get back to 360 and my horizontal displacement isn't changing much as I go vertically past this point. And if I draw that out, then I get my cosine curve. And again, the cosine curve is just my horizontal displacement from 0 as I go around the unit circle. And this is useful because lots of things go in circles. And a classic example, of course, is an engine where a piston is going up and down. The piston's going up and down, and as it's going up and down, the crankshaft is going in circles. And if you're going to actually do math on the engine, these are important things to know. And so this is the origin of why the sine function and cosine functions are important. And we will do more classes on the unit circle. This isn't the last one. Thank you.